simple harmonic motion going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in the last lesson we reviewed springs as well as sine and cosine functions in preparation for this one. So if you haven't watched that one yet, I highly recommend going back to that one before watching this one. Now in this one we're going to introduce equations for position, velocity, and acceleration of an object undergoing simple harmonic motion. We'll talk about the frequency of oscillation, we'll talk about the period of oscillation, we'll talk about the amplitude of oscillation, and we'll talk about the frequency factor. We'll talk about it both in the context of springs as well as pendulums. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. In the last lesson, we reviewed springs and looked at Hooke's law and elastic potential energy, conservation of mechanical energy, and we took a look and said if we take and extend a spring outside of its equilibrium position and then release it, so it will have a restoring force pulling it back according to Hooke's law. It'll pass through the equilibrium position and then reach a point where it is compressed by the same magnitude from which you extended it away from the equilibrium position on the other side. And then it will snap back with the restoring force taking you back through the equilibrium position and returning. So, and as long as it's an ideal spring for which there's no internal friction and no non-conservative forces whatsoever, it will just keep oscillating back and forth forever. So obviously there's no such thing as a real ideal spring. There's going to be friction or something somewhere. So, but for an ideal spring, this theoretical construct, it will just oscillate back and forth forever. And the reason we also in the last lesson reviewed sine functions and cosine functions, so is these are repeating sinusoidal functions, if you will, wave functions, that make a great model for modeling following the position of a spring in this case, or of a pendulum swinging back and forth in this kind of repetitive motion. So take a look at our typical cosine function. We start there because it turns out that the function for position is one based on the cosine. So it looks like this. So x equals a cosine omega t, and sometimes you'll see it written as x as a function of t, and that's just math jargon, so, and probably a little more proper, but we're just going to write it as x equals a cosine omega t, and the only thing that x as a function of t tells us is that t is the variable here. So we're going to follow the position as a function of time. All right, so take that x of t back off. So there's our function for position. So it follows a cosine function. Here's just simply cosine of x, or cosine of t, if you will. So, and we see that it starts at a maximum, so hits 0 at both pi over 2 and then 3 pi over 2, but hits a minimum at a value of pi, and then returns back to its original value at 2 pi. And so it repeats one full oscillation every 2 pi. Now, in the last lesson, we also learned that, well, if you put a factor in front of t here, like if we put 2t, then all of a sudden that actually means you're going to fit 2 full oscillations over the course of 2 pi. If it was 3t, we'd fit 3 full oscillations over the course of 2 pi. And so in some way, shape, or form, the period is related to this factor we put right here. And this is not a w, it's a Greek letter omega, and we call it the frequency factor. And it turns out both the frequency and the period are going to be related to this term right here. Now on the other side, we also learned that the sine and cosine functions oscillate between +1 and -1. So, but if you multiply by a term out here, which in this case is our amplitude, well, if this part of the function oscillates between a maximum of 1, well then the entire function is going to have a maximum value of a times 1, or a. So, and on the other side, it has a minimum value here for cosine omega t of -1. Well, then the entire position function would have a minimum value of a times -1, or simply -a. And that's why we call it a here for amplitude, because it is the boundaries, the minimum and maximum values that the function can take. So from a maximum value of a, and then a minimum value of -a. So when you see an equation for position of an object undergoing simple harmonic motion, the coefficient out front, you should definitely recognize that as your amplitude. So, and then we've got our frequency factor here, which we'll talk a little bit more about in a second. Now it turns out if you were taking a calculus-based physics class, this would be a little bit easier, because it turns out we're going to derive the equations for velocity and acceleration using a little bit of calculus. And I'm going to talk about that calculus, but you're not on the hook for calculus if you're taking an algebra-based physics class. But I will derive those equations using a little bit of calculus, and I will explain it because I hate just throwing equations out in the middle of nowhere and not telling you where they come from. But that's kind of the deal. So if we take the derivative of the position function with respect to time, and if you recall, we said that velocity was equal to the change in position, i.e. the displacement, over the change in time. Well, in calculus terms, we'd say that velocity was equal to the change in position over the change in time. So dx dt. And so in this case, if we took dx dt, taking the derivative of this equation with respect to time, that would get us an equation for the velocity. That's ultimately what we're doing with a little bit of calculus. And so in this case, we're going to get v equals, well, it turns out the derivative of this equation, a is just a constant. It pulls out in front of taking the derivative, and it's just going to still be a constant out in the front. But it's really just taking the derivative of cosine function. Well, it turns out the derivative of cosine is negative sine, which is why we're going to have a negative sign way out front as well. And we're going to have the sine function. So, and turns out the derivative of cosine x is negative sine x. Well, we don't just have a simple x, or in this case t, we have omega t. And when you've got an inner function and an outer function, you got to multiply by the derivative now of the inner function. And the inner function is omega t. Well, the derivative of omega t is simply omega. And so we're going to multiply by omega out here as well. And this is the function for the velocity of an object undergoing simple harmonic motion. So negative a omega sine omega t. So, and then acceleration works the same way. We said, acceleration equals change in velocity over change in time. And in calculus terms, that would be dv dt. So the derivative of velocity with respect to time. And so if we take the derivative of the velocity equation, we can then come out with an equation for acceleration. And so in this case, now it's negative a omega that's going to pull out front. So negative a omega, and it turns out the derivative of sine function is the cosine function, not the negative cosine, just the plain old cosine function. So we're going to end up with cosine omega t. But just like with the sine we did above, or the cosine we did above when we took the derivative, you also then got to multiply by the derivative of the inner function, omega t, which is simply omega. And so we're going to multiply the whole thing by another term of omega, which is why we end up with omega squared. All right, so going back now, we've got three different equations, one for position, one for velocity, one for acceleration. So we want to take a look at what amplitude means in this context, because the way we've defined amplitude, it's only actually the amplitude of the position equation. It is the coefficient out in front of the sine or cosine. Well, if we see for velocity, the amplitude is now out in front of the sine function. It's not just simply a, it's a omega. And so in this case, what that tells us is that the maximum velocity, i.e. the amplitude for velocity, is actually equal to a omega. That's the maximum value, and the minimum would be negative a omega, and the negative just refers to direction in that case. Same thing for acceleration now. So the coefficient, if you will, out in front of the sine or cosine function, in this case a cosine function, is now a omega, or negative a omega squared. And again, the negative just refers to direction. And so we can see that the max acceleration, i.e. the amplitude of the acceleration equation, is that a omega squared. Whether it's positive or negative is again just going to be dependent upon direction. So if we see our spring oscillating back and forth, if you recall, there's no force for acceleration when you pass the equilibrium position according to Hooke's law. But it reaches a maximum at the extremes when you have the maximum displacement. And that's when you're going to reach this acceleration maximum value of a omega squared. And on one, you'd make it a omega squared, and the other negative a omega squared, depending on direction. In this one, it's pointing to the right, and so you'd probably make it positive by custom. So over here, the force and acceleration would be pointed back to the left for the restoring force, and so you typically make it negative by custom in such cases. So, but these are our three equations here again for position, velocity, and acceleration. And we've got one more thing to talk about, and that's that frequency factor right here. So, and that frequency factor is related to the frequency, but it's not the same thing as the frequency. And if you recall, we talked about having, say, cosine of x. Well, I'm going to make a cosine of t this time, and then cosine of 2t, and then cosine of 3t, and talk about what the difference was. And again, if you have cosine of t, you get one full oscillation in over the distance or time, in this case, of 2 pi. Well, If you have cosine of 2t, we learned that, oh, you'd actually get one full oscillation and by the time you reach pi, and then another full oscillation and by the time you reach 2 pi, and you'd get 2 full oscillations in over the course of 2 pi. Cosine of 3t, you'd get 3 full oscillations in over the course of 2 pi. It's really just telling you how many full oscillations you complete over the course of 2 pi. So if you want to find the period, you know what, we're going to put this over here. If you want to find that period of oscillation, it's really equal to 2 pi over omega. You just take 2 pi and divide it by the number. So if it's just 1, 2 pi divided by 1, and you complete 1 full oscillation over the course of 2 pi. So cosine of 2t, again, you'll finish 2 full oscillations over 2 pi, which means you're only going to finish 1 full oscillation over a time or distance of pi, depending on your units you're looking at. And so in this case, 2 pi over 2 gets you that pi. So in the case of 3 full oscillations over 2 pi, so in that case, well, you're going to take 2 pi over 3 and you'd figure out that a full oscillation would complete in 2/3 pi, if you will. So that's how that works. That's how we find the period. Now, frequency, on the other hand, is just the inverse of the period, 1 over t. And if you rearrange this a little bit, you can see that your frequency factor is equal to 2 pi times your frequency, and we'll come back to that in a second. So if you look at frequency, frequency is nothing more than just saying how frequently something is happening. So if I start tapping my arm 5 times per second, that's a frequency of 5. We typically measure that in hertz. So 5 hertz is just 5 taps per second. And it's 5 of whatever you want to talk about per second. So, and that's what a hertz is. So 5 hertz equals 5 per second. We often write that as seconds to the -1. So in this case, we're talking about the number of oscillations per second. And it doesn't technically have to be per second. So however, for SI units, it's going to be per second. But if we talked about, how often does the sun rise? Well, 1 time per day, 7 times per week, 365 times per year. Or, if you figured out how many seconds are in a day, some very tiny fraction per second, if you went that route. So, but it's just how frequently something is happening. So if you notice, if I said that, the sun rises 7 times per week. Okay, that's a frequency of 7 per week. Well, then how long does it take for the sun to rise just once? Well, 1/7 of a week. And there's that inverse relationship. Again, if the frequency was 7 times per week, well, then the period would be 1/7 of a week, if you will, in return. So just as if F equals 1 over T, you can invert that and see that T equals 1 over F. And so again, if the frequency is 7 times per week, then the period would be 1/7 of a week, i.e. 1 day. All right, so there's that relationship there. If you know the frequency, you know the period. If you know the period, you know the frequency. But also you can see that the frequency factor and the frequency are directly proportional. So, and the constant of proportionality is 2 pi. So if you take the frequency and multiply by 2 pi, you get the frequency factor, or vice versa. If you take the frequency factor and divide by 2 pi, you get the frequency. Which makes sense because, again, frequency and period were inverse functions of each other. So if the period equaled 2 pi over omega, it makes sense that the frequency would equal omega over 2 pi. But a lot of similarities going on here. It's easy to get these confused. Spend some time really making sure you understand how to get frequency, period, and the frequency factor from each other. Okay, one more thing to talk about here. We'll need a little bit of room. All right, in the last lesson, we showed how F equaled negative kx. So for Hooke's law for a spring, the restoring force, and according to Newton's second law of motion, that's also equal to ma, and we could set them equal to each other and come up with an expression for the acceleration. And we could get negative k over m times x. Now here's the deal. When x equals 0, i.e. you're at the equilibrium position, well then the acceleration is 0. No problem there. But when you're at the extremes, either max compression or max extension, that's when x equals a, in such case, the amplitude. So, and if we take a look at that, I'm going to substitute that in, and so we can say that a maximum equals negative k over m times a. Well, we just said a minute ago that the maximum of this sinusoidal, or in this case cosine function, is a omega squared, or negative a omega squared. So in this case, I'm going to set that equal to negative a omega squared. And all of a sudden we can see that, oh, the a's cancel, the negatives cancel, And I've got an expression that says that omega squared is equal to k over m, and we've just derived that omega is actually going to equal the square root of k over m. So it is the square root of the ratio of the spring constant value to the mass that's on the end of the spring. So now I've got an expression for omega, and that's the same frequency factor that shows up here, here, and here, as well as here in the velocity equation and here squared in the acceleration equation. All right, often we say whack 'em as a way of remembering this lovely equation, and we're going to compare that in a second to a pendulum on a swing, which we say wiggle, as we'll see. So I'm going to write that one out. So wiggle. So for a pendulum, it turns out this omega is going to equal the square root of the acceleration due to gravity divided by the length of the pendulum, and we'll see where that comes from. So next we're going to look at simple harmonic motion in the context of a pendulum ever so briefly. But it turns out a pendulum doesn't truly follow simple harmonic motion. Now, if you do take this pendulum and pull it away from that perfectly vertical position, which we'll call its equilibrium position here, and then let it go, it is going to oscillate back and forth, but it turns out it doesn't truly follow simple harmonic motion. However, it approximately will follow it as long as the angle theta here that you pull it away from the vertical is less than about 15 degrees or so, and then the more it is less, the better an approximation it is to say that the pendulum is undergoing simple harmonic motion. Now, the mass we have hanging on the end of the pendulum is called the bob. So it's hanging from, some sort of wire or string or something like that of a given length, which I'll write out here, of a given length. And then it's going to be away from the equilibrium position. Instead of being away from the equilibrium position by a linear distance x, like in the case of the spring, it's going to be an arc length that we'll call s in this case. All right, now if we look at the restoring force, it's perpendicular right here, so to the length of the pendulum itself, and the restoring force is equal to mg sine theta. And that's our problem, is that as this thing gets shorter and shorter, it turns out the force modulates by a factor of sine theta, not simply theta. And that's kind of our issue of why it's not truly simple harmonic motion. With simple harmonic motion, it would adopt something similar to what we saw with Hooke's law, or at least a similar type of equation. If we take a look there, we could say that mg sine theta, can that be modeled after an equation like Hooke's law, negative kx? And the problem is, so instead of being a restoring force that's proportional to a displacement from equilibrium, it's proportional to the sine of a angular displacement instead, and that's the problem. Well, it turns out though that we have a little way to get around it, and we commonly say that pendulums follow simple harmonic motion, as long as, again, that angle theta is smaller than about 15 degrees or so. And the reason this works is that if you take the sine of a lot of angles all the way up to, say, 15 degrees or so, the sine of that angle and that angle itself are almost exactly the same value. So the sine of like 10 degrees and 10 degrees, and again, if you put it in radians anyways, almost exactly the same value. And so as a result, we can substitute this out for just simply theta. And all of a sudden now we can model this with something that's proportional to the angular displacement versus the linear displacement. So, and write this a little bit different. If you take a look, we're going to take a look at the arc length instead of a linear displacement. And it turns out there's a relationship between the arc length of the pendulum, and the angle theta. And that relationship is that L times theta is equal to that arc length. And what we really want in this equation is going to be that arc length. And so in this case, if we rearrange and solve for theta and substitute it in, we can get theta equals S over L. And so in this case, we'll take out that theta. Actually, I'll leave that in and just rewrite it. So mg times S over L equals negative k. And instead of looking at this in a Hooke's law context with a linear displacement, we're going to look at it in the context of having an arc length displacement instead, away from that equilibrium position. And all of a sudden now we can come up with an expression for k, and we can see that k is going to equal mg over L. And if we go back to the frequency factor, which was the square root of k over m, and substitute this in, that's where this is ultimately going to come for. So now omega equals the square root of k mg over L all over m. And we see that the m's here are going to cancel, and we're just left with the frequency factor equaling the square root of g over L. And that's where this comes from. And so your frequency factor for the spring is, we use whack-em to remember that, omega equals square root of k over m, whereas for the frequency factor in a pendulum, it's wiggle. So frequency factor equals the square root of g over L. One thing to note here is the mass of the bob on the end of the pendulum, the frequency factor is not affected by that at all. Only by the acceleration due to gravity, which isn't going to change unless you change planets or something like that. But only on the length of the bob, in this case, not on the mass, I'm sorry, the length of the pendulum, not on the mass of the bob instead. Cool. Besides that, though, and how we get this frequency factor, so whether it's a spring or a pendulum, you're going to get very similar looking equations for position, velocity, acceleration. You're going to find frequencies and periods exactly the same way. The only thing you're going to do different is how you get that frequency factor from some of the constants associated with the creation of that pendulum or that spring. So either with the spring constant and the mass, or from gravity as well as the length of the pendulum. Let's do some problems. All right, so the next series of questions are all going to be related to this problem right here. And a spring with a 2.0 kilogram mass attached, obeying simple harmonic motion, follows the following equation of motion. So x equals 0.20 meters times cosine of 4.0 per second times time. All right, we're going to see what is the amplitude of oscillation, what is the period of oscillation, what is the frequency of oscillation, and 3 more questions when we get there. Now, this might look a little bit different than you're used to seeing your position equation look, and I highly recommend that maybe you rewrite it without the units so it's a little easier to line up and stuff like that, but putting units in there, which is important, maybe makes it look a little less like what you're used to seeing. So let's rewrite this. So x equals 0.20 times cosine of 4.0 t, and it's a little easier to see what's going on here. And if we match this up with our equation for position, we can easily see that the amplitude, which is the first question, is equal to 0.20, and including it back here, 0.20 meters. So there's our first question. So we can also see that our frequency factor here, omega, is equal to 4.0, and in this case, 4.0 per second. Now that wasn't one of the questions. It never actually said what is the frequency factor, but the next 2 questions were what is the period of oscillation and what is the frequency of oscillation, both of which are dependent upon that frequency factor. And we can see here that the period is just equal to 2 pi divided by that frequency factor. So we'll start there. And so in this case, your period is going to equal 2 pi over 4.0 per second. And we can see this is going to come out in units of seconds then. So, and in this case, 2 over 4 is 1/2, and so we're going to get pi over 2 seconds. And so this thing's going to complete a full oscillation in just pi over 2 because it completes 4 full oscillations over the course of 2 pi seconds, if you will. All right, we're also got to find the frequency here. So, and the frequency is just equal to 1 over t. So if we already figured out that t was pi over 2 seconds, we can figure that 1 over pi over 2 seconds is going to equal 2 over pi per second. That's the frequency. So there's the first 3 questions in pretty short order found. So let's move on. Next question related to this equation says, what is the equation for the velocity? And what is the max velocity of the mass? So now we want the equation for velocity here. Well, again, velocity is just equal to negative a omega sine omega t. So in this case, we get velocity equals negative a. Okay, well, a here, again, was 0.2. So, and we're going to multiply this out, actually, because it's negative a times omega. We figured out omega was 4.0. So 0.2 times 4 is going to be 0.8. 0.80. Notice it's going to be meters per second, as it should be for a velocity, and then times sine of omega t, so 4.0 per second times time, whether we include the units or not. All right, so there's the velocity equation, and then we wanted the max velocity. And if you recall, the max velocity is just the amplitude on the front, the a times omega, which, because I already multiplied them together, is evident right from the equation. And that max velocity, actually, I'm going to write that over here. Max velocity is just simply going to be 0.80 meters per second. It's the amplitude of that velocity equation, which is just the coefficient out in front of the sine function. All right, finally, next question says, what is the equation for the acceleration and what is the max acceleration of the mass? And so in this case, we've got negative a omega squared. So and in this case, we did a times omega, and it was 0.2 times 4. Now it's going to be 0.2 times 4 times 4. And so in this case, 0.2 times 16, well, 16 times 2 is 32, so 16 times 0.2 is going to be 3.2. And notice now it's going to be meters per second, which is meters per second, or meters per second squared, the proper SI unit for acceleration. And then cosine omega t, so cosine 4.0 per second times time. All right, the other half of that question was, what is the max acceleration? And the max acceleration, again, is just equal to the coefficient out in front of the acceleration equation, a omega squared, which we already calculated to be 3.2 meters per second squared. We're good to go. Now, one last part to these last two questions. It's not actually in the question, but I want to know, where do we reach this max acceleration? Where do we reach this maximum velocity? Well, you might recall that max velocity is reached on an oscillating spring when you pass through the equilibrium position, where the max acceleration and the max force are both reached at the extremes, either max extension on one end or max compression on the other hand, in either case when you have maximum displacement. All right, last question related to this is, what is the maximum value of the restoring force and where does this occur? And again, that max restoring force is still going to happen at the extremes, either when you have a maximum displacement, either compression or extension. But now we want the maximum value of that restoring force. And so in this case, it's not one of our traditional equations. Notice force is nowhere up here, but you guys do know a couple different ways we could calculate this. So we could calculate this with Newton's second law. And if I want the maximum force, well, then I want the maximum acceleration. That'd be one way to go about it. Or we could try to use Hooke's law, F equals negative kx. And ultimately, either one is going to get you the right answer, but one's a little easier to do than the other. Now, we're told the mass here is 2.0 kilograms, and we just figured out the max acceleration was 3.20 meters per second squared, and so this is an easy one to use. So 2.0 kilograms, let's write that out, times 3.2 meters per second squared. So in this case, it's going to get us 6.4. I'm going to erase Hooke's law and rewrite it if we need it. 6.4 newtons. Now, could we have used Hooke's law to figure this out? Yes, it just would have been a little more of a pain in the butt. So if we do that up here, let's say, so F equals negative kx. And the problem is we don't have the spring constant. It wasn't given in this problem. And it didn't need to be given because everything else you need actually is given. And if you recall, Wacom here tells us the relationship between the frequency factor, the spring constant, and the mass. And we know both the frequency factor and the mass, so we can calculate out that spring constant. So omega equals the square root of k over m. So, or we could say that omega squared times m is going to equal k. And so in this case, omega again was equal to 4.0, so squared is going to be 16. And then times the mass of 2 tells us that k is going to equal 16 times 2 is going to be 32 newtons per meter for our spring constant. And now we could use F equals negative kx if we knew the maximum displacement. All right, well, how do we get that maximum displacement? Well, again, that's just the amplitude of the position equation. That maximum displacement is 0.2 meters. And so if we took our spring constant, F equals negative kx, so multiplied it by that maximum displacement of 0.2 meters, we would once again still get 32 times 0.2. So 32 times 2 is 64, so 32 times 0.2 is still 6.4 newtons. We find out that the max force is once again the same answer we got. A lot easier to have gotten it using Newton's second law, though. All right, one more problem, and this one's going to be more related to a pendulum. So in this problem says, if the length of a pendulum is increased by a factor of 4 and the mass of the bob is doubled, what will be the effect of the frequency of oscillation? Now, I've asked this one on purpose, and I've told you that I've changed the mass, and you should be like, Chad, you told me mass doesn't matter. And yes, for a pendulum, the mass does not matter. Your frequency factor here only depends on the acceleration due to gravity and on the length of the pendulum, not on its mass. And you might recall, well, why is a pendulum swinging back and forth? What's causing it to want to return back to equilibrium? Well, it's gravity, that is. So, and if you recall, the acceleration due to gravity for any object on Earth, as long as we're ignoring air resistance, is 9.8 meters per second squared. It doesn't care about the mass. And if gravity's in charge of the restoring force for a pendulum, then it shouldn't be too surprising that the mass of the bob doesn't matter. All right, so if the length of the pendulum is increased by a factor of 4, and the mass of the bob is doubled, so notice gravity wasn't changed. So what will be the effect on the frequency of oscillation? So a couple things you need to remember here is that the frequency factor is proportional to the frequency. And here we can see that the relationship between frequency factor and the length is that, and I put approximate, let's get proportional in there. It's proportional to the square root of 1 over L. And therefore that's going to be proportional to the frequency. Well, what did we do to L? Well, we can see that as L goes up, the frequency and frequency factor are going to go down. There's an inverse relationship. Not inversely proportional because of the square root, but there is an inverse relationship. And so it shouldn't be too surprising that if we made the length of the pendulum longer, it goes up. Now, the school I used to work at, we had a pendulum that was several stories tall, and it moved so unbelievably slow. And it's easy for me, therefore, to see that, oh yeah, as you make the pendulum longer and longer and longer, it should make the frequency slower and slower and slower, if you will. So, or lower and lower and lower, more proper. So in this case, if the length goes up by a factor of 4, then the frequency factor and frequency should go down not by a factor of 4, but by the square root of 4. So go down by a factor of 2, i.e. they are cut in half. And that is the answer to that last question. If you have found this lesson helpful, consider giving it a like. Happy studying.